Good evening. Welcome back to the session. Today we'll talk about the kinematics of the fluid. In the kinematics of the fluid, we'll discuss about the motion analysis of the fluid particles. Until now, in this condition, previously we are talking about the fluid is at rest condition. So that is under the fluid static portion. Here we'll discuss about the fluid is in motion. But the motion characteristics only we'll discuss about here. But what is the cause for this motion? This has been discussed in this portion. So kinematics, analysis of the kinematics of the fluid. We'll talk about the motion, geometrical motion of the fluid. So as the fluid is under motion, so you know the fluid element is undergoing some deformation. So it may be the linear deformation, it may be the angular deformation. Otherwise, the fluid element is going by translation. So these are the things we'll discuss in this portion, kinematics of the fluid. So that will come directly to the slide here. So in this slide, so here we'll see the preview and basic idea of kinematics of the fluid. So kinematics of the fluid is the motion analysis. Will come here. So we'll talk about the motion analysis. So motion analysis of fluid. So in the motion analysis, the geometrical motion. Actually, it's better to write it down, the geometrical motion. Because if the fluid element, if you take some fluid element, as the fluid is undergoing motion, so it will go for the continuous deformation. Geometrically, it will go for the continuous deformation taking place here. So geometrical shape is continuously changing here. So this analysis will go for it. So whether this deformation analysis we are talking about here, deformation. Deformation, there is two types of the deformation. One type is the linear deformation. Another type is the angular deformation. So linear deformation, we'll see one by one this portion. Linear deformation means the length is increasing, or according to the lengthwise it is increasing. So that is the linear. It under the linear. Angular will be this angular changes is occurring due to the shear stress. That is the angular deformation. Other than this, there might be the motion, it's caused the translation. Just like a solid body. It may cause for the translation. It may cause for the rotation. All this analysis will have to do with this geometrical sense rotation. All this kind of the analysis we'll do in this portion. Kinematics, under the kinematics of the fluid. But here we'll not consider here what is the cause of the motion. Cause for this motion. For this motion. This thing will not discussion in this portion. What is the cause for this motion? That means the force or any moment or torque will not discussion this portion. Simply geometrical analysis will do. And motion characteristics, in the case of the motion characteristics figure, how we characterize the motion, whether the element is displacement having, or rate of displacement, which is known by velocity, or rate of change of velocity, which is known by the acceleration. This analysis we have to. So motion characteristics, parameter. Like velocity, acceleration, and displacement. These are the things we have to discuss in this topic. Now, the fluid particle concept is coming. One concept is coming, that is the fluid particle. What does it mean by the fluid particle? Concept is coming as a fluid particle. Why the particle concept is coming? Because to know about the velocity, we have to track some particle. This description is under the Lagrangian description. So if we track first you leveled one by one particle, leveling through the initial position and time. If you level a particle with its initial position and time, and then you track it, whether the next second where it is location, or the next second where it is location. In such a way, if you're tracking a particle, so hence the particle concept is coming, fluid particle. So fluid particle, if you define the fluid particle, is a collection of molecules. Fluid particle, whenever we are telling about it, is a collection. Fluid having a collection of molecules. This collection of the molecules having the same group behavior statistically. Statistical average sense, if you're taking the statistical average sense, it having these molecules having the same group behavior. Having same group behavior. Here on statistical average sense. On statistical average sense. So those particles, fluid having an enormous number of molecules, these molecules having a same group behavior on the statistical average sense. Okay. Then this is just like this molecules is behaving just like an inert pressure. This molecule is behaving like an inert pressure. That means if you inject any dye over the fluid and it is so inert that it cannot be react with the fluid, as well as it having a same density with the fluid. As they are the same density with the fluid, so no buoyancy force will be act during the fluid and the motion. Since this kind of the particle is known as the neutrally buoyant particle. This kind of the particle is known as the neutrally buoyant particle. So that means the fluid particle having the same density with the flow. So whatever the position, it should maintain the same position. So according to the position wise, it will not change. It just track the flow. So the velocity of this particle at any point and velocity of the flow is the same. It is just captures the flow velocity. This kind of the particle is known as the neutrally buoyant particle. So again, I'm telling the fluid particle, we are considering the fluid having an enormous number of molecules. The molecules on the statistical average sense having some sort of the group behavior. Then what is happening? This kind of the concept is taken as the fluid particle. It is just like behave like an inert pressure. It is the particle is behave like a inert pressure. For the tracing purpose, if you inject some dye, it looks like a dye. Some dye, if you inject the dye inside the fluid, how it will behave? The fluid particle is behaving the similar way. And it is as inert that there is the same density with the fluid. This particle having the most important term is this particle having the same density with the fluid. If the particle having the same density with the fluid, there is no buoyancy force. There is no buoyancy force. So it will be remains at its own location and it will goes along to the flow. This kind of the particle is known as the neutrally buoyant particle. This kind of the particle is known as the neutrally buoyant. neutrally buoyant particle. This kind of the particle is known as the neutrally buoyant particle. Now consideration is the neutrally buoyant particle having the same velocity of the fluid velocity. Neutrally buoyant particle having the same velocity of the fluid flow velocity. So at any place, what is the flow velocity? The particle velocity is the same. No changes. The particle motion characteristics is the same. This concept we'll see the next two topics we are going to discuss according to the description, how we describe this motion. So two description is that. That is, first one is the Lagrangian description. In the case of the Lagrangian description, we are tracking the particle. In Lagrangian description, we are tracking fluid particle. Very simply, I'm telling, we are tracking the fluid particle. How to track? First you level about its initial position of the particle, initial position and time, initial time. First you level it. After level, you see along with the particle is flowing is like that, and after t time, the particle comes here. Previously, at here it is initially it was at here. After some time, the particle is coming at here. After some time, after time t. So in this position R, in the position R is the function of initial position, that is R0 if it is. So it's a function of R0 into at time t. At time t it is coming. So this way we are leveling and going to know that where is the location of the particle. So individually, one by one particle we are tracking in this description. It is too much tedious because you think about it, why it is complicated? Because the fluid having an enormous number of molecules or particles like the solid. And each molecules or particles are undergoing continuous deformation. So it is very much difficult to track such of the cases. Hence, the Lagrangian description is not used that much because to track individually particle is very much tedious. But if we are comfort, there is a less number of particles is there. So particle concentration on the flow is less. So then we can go approach for the Lagrangian description. So that is the case. So Lagrangian description cases, it is actually this is nothing but the control mass analysis. In the Lagrangian description, we are talking about control mass analysis or system analysis. Control mass analysis or system analysis, control system analysis. It is a kindly difficult job because to tracking individual particle you are tracking and getting its, you take it the path, which path it is individual particle is following up. It is a difficult cases. So in the case, next description, we will talk about the Eulerian description. Eulerian description, you choose a particular position. You are choosing a fixed position or some portion you are choosing like it. Okay, now you are so many molecules is coming through this position. So you make the position, some local position you are making it. Some local position you fix it. You fix here in the Eulerian description some local position. As you could be able to fix here the local position, now what you are doing it, whatever the particles is coming through this zone, you are only tracking this particle. Whatever the particle is coming through only this zone, you are only following up this thing. Which particle is not coming in this zone, you are not following it. So this kind of the description is the Eulerian description. So you set up a control volume. So this approach is the control volume approach. You set up a control is a control volume approach. You set up a position in here. So as you set up a position in here, so then it is happening. Control volume approach. So you fix a local position, local zone, and whatever the particle is coming. So by this way, previously Lagrangian description, you are getting the particle velocity or particle acceleration, particle velocity. By these cases, you are getting fluid particle. Here, you are getting entire flow velocity. Flow velocity. That is the difference. This two description is different. In the physical example, if you are tracking some person, you individually tracking in a school, you are individually tracking some sort of the persons, one by one person. You are tracking from their initial position and where they are going, whereabouts you are tracking. It is very difficult for, if the number of person is more, it is very difficult to track of everyone. But Eulerian description is how it looks like. You just fixed one zone, and how many person is entering this zone and going out from this zone. You are checking the behavior of this person. So this is much more simpler than the previous one. So this is the here is simpler. This app description is the simpler than previous one. Okay. Here, the local position and time. Velocity, the flow velocity, we are considering here the flow velocity. Here we are talking about the particle velocity. But this both description, Eulerian description or Lagrangian description, are interconvertible. You can convert control mass analysis to the control volume analysis. Similarly, control volume analysis to control mass analysis. So these two approaches are interconvertible. Interconvertible. You can convert both description in here. Okay, so that is because Lagrangian description, the most difficulty, if a system, the concentration of the particles is more, it is very difficult to get individual particle analysis. So that is why we are much more, it is easy to take the Eulerian description because it is a control volume approach. You fix to one zone, and what are the particles is coming into the zone? We are talking about this particle. We see the behavior of the particle. We see the flow acceleration in the corresponding zone. Okay, so that is the analysis we are talking about here, description of the motion. So motion characteristics, I am telling you, the motion characteristics, there are the velocity and acceleration is the motion characteristics. So motion characteristics parameter is the velocity or acceleration. You can talk about the displacement also, but basically we are more interested to getting the velocity, and if we know the time, so we multiply it and getting the displacement also. So velocity, it's a maybe the velocity or acceleration, both are depends on the space or spatial coordinate. Spatial coordinates like X, Y, Z, and time. Both are dependent on spatial coordinate and time. Both are the function. The velocity is the function of the spatial coordinate and time. So this is the cases. So what we get? The velocity V is a function of X, Y, Z, the spatial coordinate and time. Similarly, the acceleration is also the function of X, Y, Z. In the Cartesian, it is a case of the Cartesian coordinate. Cartesian coordinate system. That's why X, Y, Z we are taking care. If polar coordinate system, so you have to go for the R, theta, Z in this way. Or spherical coordinate system, you have to go for I, R, phi, theta in that way. So this is the case we are talking about here. Now some kind of the flow analysis, the types of the flow. First, the types is a steady flow. We'll see the steady flow. What does it mean by the steady flow? The steady flow is, in the steady flow, it is a, if you fixed one position, if you fixed the position, some position is fixed. Okay. Then you see the fluid motions are time independent. Motion characteristics are time independent. It does not depend on the time, the flow characteristics and motion characteristics. So flow characteristic is the same, velocity and acceleration. Flow character, time independent flow characteristics parameter like velocity, acceleration, and fluid properties or hydrodynamic properties. Fluid properties like density. Okay. This kind of the properties, pressure, density, viscosity, these are the things. But here, pressure, density, viscosity, these are the properties. So here, time independent, you see here, that is the time independent characteristics. That means the velocity does not depend on the time. The velocity here may be the function of x, y, z, but it is not a function of time. Similarly, the acceleration is also maybe the function of x, y, z, but it is not a function of time. Density, all the cases, the same thing. So it may be the function of x, y, z. So if you change x, y, z, that means spatial coordinate, it will changes, but time independent. It does not vary with the time. That is kind of the flow is known as the steady flow. So time independent flow characteristics parameter and fluid properties, this kind of the flow is known as the steady flow. Next, the similarly opposite of the steady flow is the unsteady. The opposite of the steady flow is known as the unsteady flow. Simply opposite. What does it mean? That it is a time dependent. It depends on the time. It is varying with the time. So the same flow characteristics parameter and fluid characteristics parameter is varying with the time. Same flow characteristics and fluid characteristics is varying with the time. This is the concept we are taking here. So this is concept. It is a time dependent flow. Time dependent flow. So same thing, flow characteristic parameter and fluid properties. This kind of the steady flow and unsteady flow. Now next two type of the flow is there. That is the, that we will see. That is the uniform flow. That is the uniform flow. Uniform flow, we might have discussed in the your viscosity portion, the plate analysis, whenever doing the sleep and no sleep condition, that time we talk about the uniform flow slightly. So uniform flow, that is the you fixed the time here, some fixed time, and you analysis. And what you come to know, that is the fluid flow characteristics parameter. Fluid flow characteristics parameter. Fluid flow characteristics parameter means same velocity and acceleration. It is not the function of x, y, z. It does not depend on the position. So if you change the position, there is no change of the flow characteristics parameter. So fluid flow characteristics parameter, velocity or acceleration, is not a function of x, y, or z. It may be a function of time, but x, y, z does not depend with the x, y, z or spatial coordinate. So it's better to write it position independent flow. Position independent flow. So it does not depend on the position. If you change the position, the velocity will not change, acceleration will not change at a corresponding time. That means at an instant of time, if you see, everywhere there is a same velocity. This kind of the flow is known as the uniform flow. So similarly, the opposite of the uniform flow is the non-uniform flow. That is the position dependent flow. That is the position dependent flow. So we have got some idea about the position dependent flow, and so we'll see in a analysis in the very particular way. So first flow, we are taking it here, that is the steady flow. Second, unsteady flow. Third, uniform flow. And non-uniform flow. Non-uniform flow. So this kind of the fourth flow, the fluid properties. So here, if you write it, the fluid properties and flow characteristics parameter. Fluid properties and flow characteristic parameters. So it's the time, whether it is varying with time or space. So here, the steady flow, it does not vary with time. Unsteady flow, it might vary with. So steady flow, it does not depends on the time. So a particular position, at time 1 second, what is the velocity? The time at 2 seconds, the same velocity. Time at 3 seconds, the same velocity. If you consider a particular position, at time 1 second, what is the velocity? Time 2 seconds, the same velocity. 10 seconds, same velocity. 100 seconds, same velocity. No changes at a particular position. If you change the position, there may be the change of the velocity, but it does not depend on the time, the similar. Unsteady flow, there is no time dependence. Uniform flow, it is a no space, position independent. Uniform flow is position independent. So in this case, time independent, in this case, the position independent. That is the thing. The analysis is here. Now, if you consider steady and uniform flow. Both steady. Steady means time independent. Uniform means position independent. So velocity is constant at each time and each space, the same velocity. That is a consideration. This is kind of the case. This kind of the case. Only we are writing steady flow. It is better to write it steady flow, but non-uniform. Because it is depends on the space. It is varying with the space. Steady flow can be a non-uniform flow. And the similar way, uniform flow can be unsteady. But if it is a steady and uniform flow, it does not, velocity is ever constant at every point in the flow field. At every point of the flow field. Flow field is such a definition. You have heard about the flow field, any field definition. So each and every point you can get the velocity. Then you got the field of it. Each and every point you can analyze the velocity and you've got the field, development of the field. That is the flow field. So this is the types of the flow. A steady flow can be non-uniform. A uniform flow can be unsteady flow. But if the flow is steady and uniform, then the velocity or flow properties or fluid properties will be ever constant at every position, at every time. That is the consideration.